Hello, Honors Chemistry, and welcome to Chapter 6, Section 6.3, Counting Atoms by the Gram. So really in 6.2, right, your book introduces the concept of new conversion factors. Yes, how can we relate two things, right, via a new conversion factor, right, which really is just, all we're doing is extending the stuff we started talking about in Chapter 2, right? We can relate two quantities as long as there is one or a series of conversion factors that will take us from point A to point B, or from our given to our goal, right? Which is what most of chemistry is, right? And so the new conversion factor for this section is the concept of the mole, yes? Where a mole is just a defined number of particles, right? And it's defined by Avogadro's number, which is 6.022 times 10 to the 23rd particles, right? Equal to 1 mole of a pure substance, right? And we do abbreviate mole, MOL, right? I know it's not a significant abbreviation, but that's the abbreviation. And we use this word the same way we use the word dozen, right? When we say 1 dozen, you automatically know I mean 12, right? Or if we were being fancy and we were saying a baker's dozen, you know I mean 13, right? Or if we say decade, you know I mean 10, right? Same principle. When I say 1 mole of atoms, you know I mean 6.022 times 10 to the 23rd atoms, right? And so that means we need to be mindful about our particle words, right? Then this goes back to chapter 5, where we talked about atoms, right? If we're talking about an element, atoms would be the appropriate particle word, right? If we're talking about either a molecular element or a molecular compound, molecule would be the appropriate particle word, right? Although that could also be broken down into atoms, depending on what we're using here, right? Formula units, if we're talking about what kind of compound, correct, ionic, right? We could even be talking about ions if we were breaking down our formula units, right? All of these words could stand in for particle, yes? All right, so just be mindful about that. And note that 1 mole is defined, right, like in land of chemistry definitions, right? It's defined by the number of atoms in 12 grams of carbon-12, yes? And so because there has to be a standard reference for everything, right? And that just is the standard reference, right? So then, this is all the same answer, right? So what is a mole? A mole is that number of particles, right? And Avogadro's number is that particles. So those all go together. Now, one thing to be mindful of, right? So it's just a number of particles. That's what a mole is, right? So just like I could have a dozen small eggs or a dozen extra large eggs, right? I could have a dozen bagels or I could have a dozen steaks, right? They're all going to be different in terms of how much space they take up, how much mass they have, what they look like, what their properties are, right? All I'm saying is how many of them I have, right? Same thing with the word mole, right? 1 mole of copper atoms versus 1 mole of helium atoms, right? So both of those represent 1 mole of atoms of elements, right? But how much space they take up, what their properties are going to vary. The only thing they have in common is the total number of particles, yes? As in, they both have 6.022 times 10 to the 23rd particles, right? Likewise here, right? It's a sample of sulfur and a sample of carbon, right? And we're using grams to measure them out, right? And 1 mole of each, again, different amount of space, different mass, different properties. So then that brings us to how do we get to this gram value here, right? And that's going to go back to our molar mass, right? Which I didn't put on this page for some reason, right? But thankfully there's space for it. So molar mass. Moles, or Avogadro's number, are the conversion factor between particles and moles, right? Now, in order to talk about mass, we use molar mass, okay? Where molar mass is by definition, right, the mass of 1 mole of whatever it is that we happen to be talking about, right? Now, conveniently for us, the mass of 1 mole of whatever it is that we're talking about is conveniently defined by the periodic table, right? So if we think back several chapters to chapter 3, right, we talked about, for example, how, let's look at beryllium, right? So beryllium has this number on the bottom, right, which in this case is 9.0122. And we talked about previously how AMU, right, 1 atom of beryllium, right? So 1 atom of beryllium has a mass of 9.0122 AMU, right? Where AMU was a scaled down version of kilograms, right? I think something on the order of 10 to the negative 27th kilograms, right? and that was the mass of one atom. Turns out that that number does double duty, right? If we scale up from AMUs to grams, it also turns out that 9.0122 grams are equal to 1 mole of beryllium, right? We could work out that conversion, right? So basically we scale our atom from a singular atom up to a mole of atoms. We scale our AMU from AMU, which is 10 to the negative 27 kilograms, up to grams basically, right? And we end up with this relationship, right? So that same number that does the mass of an atom in AMU does the mass of a mole of atoms in grams, yes? So a mole of neon atoms has a mass of 20.18 grams. A singular neon atom has a mass of 20.18 AMU. Yes, does that make sense? All right, so then if we go back to our slides here, right, that's where this information comes from, is from our periodic tables, okay? So let's go ahead and do our skill builders really quickly. So how many gold atoms are in a pure gold ring containing this many moles? So my given is moles, right? My goal is atoms. So I just need a relationship between moles and atoms. Oh my gosh, what is that? Ding, 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 Avogadro's number, right? So this one is pretty simple. And so then for every 1 mole of AU, there are 6.022 times 10 to the 23rd atoms of AU. Yes, moles cancel, atoms of AU are all that's left. And then I just need to make sure I do the math correctly. Yes? All right. Next up, calculate the number of grams of sulfur in this many moles of sulfur. So my given is moles of sulfur. My goal is grams of sulfur. Do I know a relationship between moles and grams? I do. Molar mass of sulfur. Sulfur has a molar mass of 32.06. And remember, that's the number of grams equal to 1 mole of sulfur, right? So let's just set this up, 2.78 moles of sulfur. And I'll put each piece where it belongs. If this says moles, that needs to go down there. Moles of sulfur cancel. Grams of sulfur are all that remain. I would do my math and round to the correct number of sig figs, which is, right, 3. All right. Calculate the mass of this many helium atoms, right? So my given is atoms. My goal is mass. What do we notice here? Right, this one's a tiny bit more thoughtful, right? In that there is no direct conversion between atoms and mass, but I can go from atoms to, correct, moles, and then to mass, yes? So I can use multiple conversion factors. So we have 1.23 times 10 to the 24th helium atoms. And so here it's good to notice the size, right? So here this is, so thinking back, right? So this is not even 1 mole. So we would expect that the number of atoms represents not even 1 mole, right? Here in this particular instance, we have almost 3 moles, so we should expect this to be, the final answer to be almost 3 times the mass of 1 mole, right? Here, this might seem like a boatload of atoms, and it is, right? Consider 1.2 times 10 to the 24th, that's approximately 2 times 6.022 times 10 to the 23rd, which means it's about 2 moles. So we should expect that our final mass should be the mass of approximately 2 moles, right? So it's always good to check the number sense as you do your math. It'll help you to make sure you don't make mistakes. So anyway, atoms is down here, which means if I think about Avogadro's number, right, my particle unit needs to be on the bottom, right? So 6.022 times 10 to the 23rd atoms of helium is equal to 1 mole of helium. Now I need to go look at my periodic table. Which says 4.00. All right, and then we would just do our math and we would come up with the right answer. Yes, does that make sense? Okay, So things to take note of, right? All of our conversion factors, like they have all year, right? We put the piece wherever it needs to go to cancel, right? And this number is always going to just get taken from our periodic table. So this is one of those times to take note that we have the right mass on our periodic table. So anytime you notice that one of your masses are off, please go and fix it so that you can have the right one. All right, and our just for fun problem. If you can count 3 numbers per second, what is that really? 3 numbers per second. That's right. That is a conversion factor, yes? 3 numbers per 1 second, yes? It's a relationship. And when we see the word per, what that really means is equal. There are 3 numbers equal to every 1 second, right? How many years, right? So that's clearly our goal. Would it take to count 1 mole of M&Ms, right? And this is our given. So if we look here and we dissect the problem, right? So sometimes if a problem has several numbers in it, it's easy to get lost in determining where to start, what number to start from. But here, once we dissect this, right, numbers per second, this is a conversion factor, right? That's not a given. That's not a place to start. This is where we start, right? Does that make sense? And this is a piece of information that we'll employ somewhere along the way, right? So if I have 1 mole of M&Ms, obviously I need to get out of moles of M&Ms, right? So let's go from 1 mole of M&Ms to 6.022 times 10 to the 23rd M&Ms, right? And if I can count, I should have said I can count 3 M&Ms per second, right? So let's say I have 3 M&Ms per every 1 second. And then I know that there are, say, 60 seconds in 1 minute. And I know that every 60 minutes makes up 1 hour, and I know that 24 hours make up 1 day, and I know that 365 days make 1 year. Then I just need to solve. And we would get 6 we'll just say 6 times 10 to the 15th years. Yes? It would take you multiple lifetimes to count 1 mole of M&Ms, and that's at a rate of 3 per second. And then obviously, even if we doubled, tripled, we could change it by an order of 10, right? And this is not going to go down by a whole lot. Yes, does that make sense, right? Just to sort of emphasize the enormousness, right, of what 1 mole is, okay? All right, thank you for listening. Stay tuned, and in the next video, we will talk about chemical formulas as conversion factors. All right, thanks for listening. Be good, and I'll see you soon. Bye.